Greetings. This video is the second of 3 videos on descriptive statistics. When we describe a dataset, our primary focus is on obtaining measures of central tendency, measures of variation, and graphing the shape of the distributions of variables. Measures of variation are statistics that describe how far apart the values of data points are from each other. In other words, they capture the spread of a variable. In this video, I will introduce 4 common measures of variation: range, sum of squares, variance, and standard deviation, along with frequency measures. Range is the simplest measure of variation. After sorting the values from low to high, the range is the distance between the highest score and the lowest score. For a variable age with values 10, 12, 13, 14, 14, 15, 15, 15, and 18, the range is 18 minus 10, which is 8. Or it can be expressed as from 10 to 18. Range is a rather crude measure of variation and has a serious limitation. It's highly sensitive to extreme scores. For example, if 18 were replaced with 118, the range would become 108, stretching from 10 to 118. You may recall the term sum of squares from when I introduced the 2 properties of the mean. Let's revisit that concept with the age example. Mathematically, the sum of squares is the sum of the squared deviation scores around the mean. After calculating each deviation score, squaring it, and summing them, we obtain a sum of squares of 40. Sum of squares is not a popular measure of variation because it has 2 problems. First, sum of squares always increases with the sample size. Second, the squared values are difficult to interpret. With that being said, sum of squares is an important concept to understand. Not only will we encounter it frequently in inferential statistics, but it also forms the foundation for the next 2 measures of variation. Variance was developed to address the problems with sum of squares. Because sum of squares always increases with sample size, variance is calculated by dividing sum of squares by the number of observations. The variance of a population is denoted by sigma squared, while the variance of a sample is denoted by S squared. A key point to remember is that population variance is calculated by dividing sum of squares by the population size, whereas sample variance is calculated by dividing sum of squares by n-1. Here, the n-1 is called the degrees of freedom. Using the age example, clearly based on a small sample, the variance is the sum of squares divided by n-1, which is 40 divided by 7 equals 5.71. Variance is not affected by sample size, but it still has the drawback of being expressed in squared units. To address this, statisticians take the square root of the variance and call it the standard deviation. Standard deviation is the most widely used measure of variation. It's denoted by sigma for population and S for samples. By taking the square root of the variance, standard deviation converts the value back into the original measurement units, making it easier to interpret. Conceptually, the standard deviation represents the average deviation of individual scores from the mean. You will see that it is a very important concept when we discuss the normal distribution in the next chapter. The four measures we have discussed so far, range, sum of squares, variance, and standard deviation, are all for quantitative variables. Range requires values to be sorted, and the other three requires a mean to be calculated. But what about nominal variables? Since their values cannot be sorted and the mean cannot be calculated, the only way to capture variation is through frequency distributions. Frequency refers to how many times a value occurs in a variable. In some places, frequency is also labeled as count. For example, in the age variable, the frequency of 12 is 1, the frequency of 14 is 2, and the frequency of 15 is 3. Tabulating these counts gave us a frequency distribution table. For qualitative variables, where the number of possible values is usually small, frequency tables are the best way to summarize variations. For instance, if a data set has 60 students with 30 girls, 29 boys, and 1 student identified as non-binary, the frequencies and the percentages can be presented in the table like this. Can we use frequency tables for quantitative variables? Yes, but only when the number of values is small. For interval or ratio variables with many possible values, the data must be grouped into manageable, equal-sized intervals without distorting the distribution. For example, test scores in this table are grouped into intervals of 10 points, from 60 to 69, 70 to 79, all the way to 130 to 139. At the extremes, categories such as below 60 and above 140 were added to capture outliers. In both qualitative and quantitative frequency tables, a cumulative frequency column may be included. Cumulative frequency shows the number of observations at or below a given value. It's calculated by adding each frequency to the sum of its predecessors. In this table, the first category is females, and the second category is males. So the cumulative frequency of males is 30 females plus 29 males, which is 59. Dividing cumulative frequencies by the total number of observations converts them to cumulative percentages, which explains why the cumulative percent of males is 98.3%. The result of dividing 59 by 60. The percentage column shows relative frequency, which is the proportion of observations for each value. It's calculated by dividing the frequency counts by the total number of observations. Let's end this video with a brief summary. Sum of squares, variance, and standard deviations are only applicable to interval and ratio variables. Range can also be used for ordinal, interval, and ratio variables. For nominal variables, the only way to describe variation is with frequency tables. Frequency tables may also be used for quantitative variables, but only when the number of values is small. Otherwise, values should be grouped into intervals.